start. So the basic intention of designing a rocket is to rocket nozzle is to produce high energetic gas that can come through the exit by burning high energetic propellants, that high energy material which is burned inside the combustion chamber and which produces high ejection gas, which is accelerating through the rocket nozzle, which produces a thrust. So that is the main intention of this design. Okay, in order to have large value of specific thrust, the kinetic energy of exhaust gas must be large enough to produce higher exhaust velocity. So higher exhaust velocity is one of. So for that, the pressure ratio across the nozzle controls the expansion process. Okay, so we can achieve maximum thrust in a given engine only when the exit pressure PE is the same as the ambient pressure. That means optimum expansion condition. If PE is equal to P atmosphere, that means the pressure thrust component, because we have two thrust components. One of the thrust is the momentum thrust, and the second thrust component is the pressure thrust. So once PE is equals to PA means ambient pressure, then the pressure thrust component becomes 0. And that is known as the optimum expansion of nozzle. So that is our intention. Okay, so generally, two types of nozzles are there. One is convergent nozzle, and another is convergent divergent nozzle. So these are two types. Convergent divergent nozzle represented is CD. Okay, so which are used to produce thrust in the jet engine. Okay, so CD implies nozzles are mostly used for producing thrust in the rocket engines. This convergent divergent nozzle type. How was the fundamental flow take place in the convergent divergent nozzle? That is our question. Okay, so in such case, let's come to the nozzle. So this is a what we call combustion chamber here, which is represented with number 1. And after nozzle, at the end of nozzle, we have a section having Mach number less than 1 point. This is Mach number less than point means divergent position. The divergent duct start from after combustion chamber divergent section, and in the divergent section the Mach number is less than 1. That is subsonic flow of the velocity is highly less there, but high pressure is there. Okay, the pressure and the velocity are inversely proportional. If there is high velocity, pressure is less. Okay, so this is the divergent region, no, convergent region. And at the mean position, there is a very narrow section of the nozzle known as thrust. At the point of thrust, the Mach is equal to 1. Mach is 1 means the sound speed at that particular position is equal to the speed of the particle that is coming through the convergent duct of the nozzle. And then once it passes this point, high acceleration, high velocity will take place. Pressure is less, velocity is high here. Okay, here pressure is low, velocity is low, pressure is high around here. Okay, so this is the area at which Mach 1, or known as the throat area, is represented with A star. You can see here A star. So this A star is a throat area. Sometimes you can put it AT. AT means throat area. Okay, and at the exit, this is the point where exit pressure PE is located. So if PE is equals to P atmosphere, atmospheric pressure is somewhere here outside of the system. So once it is equal to then what we can get is the optimum thrust. So that is the design concept of this thing. So what another important thing, yeah, P at T2, okay, throat pressure. This is atmospheric. It is just P at PB means exit pressure. So this is the flow feature in convergent divergent nozzle. How it flows. At the throat, P over PT2 is somewhere is 1. We have actually 3 different region A, B, C, and also D, E, F, which are there. So this is just the exit phenomena. It indicates exit phenomena. And this dotted line indicates the throat phenomena. And this is inlet position, means the high pressure gas coming into the throat. So this is just an inlet phenomena. At inlet, at throat and exit. So these locations are, location 2 is inlet. Location 1 is the throat. And location, this you can represent with E or with 3 number or any kind of representation you can show. Okay? So this is the phenomenon of convergent divergent nozzle. So let's calculate exhaust velocity. Okay? Means how we can formulate those exhaust velocity with respect to enthalpy, entropy, CP, temperature, velocity, and so on. So let's come to some important formulations. So generally, the flow in convergent divergent nozzle is 3-dimensional in nature, and the temperature, pressure, and composition of gas vary along the length of the nozzle. Means this composition is related with the density. Okay, so wherever there is pressure change or temperature change, there is composition change also. These things are varying along the length of the combustion chamber, from combustion chamber to the exit. So for that, we have some kind of assumptions. Actually, the actual flow is 3-dimensional, or the actual nozzle is 3-dimensional in nature, but the flow we call steady 1-dimensional isentropic flow we consider. We consider some assumptions. Okay, so what are the assumptions considered for this ideal purpose? Okay, one is the steady 1-dimensional isentropic flow is considered. The second, the working fluid is homogeneous in nature, means there is no heterogeneity in the fluid. The fluid means the gas particle which generated from high ignition phenomena are considered homogeneous. And the amount of mass due to condensed phase, that means liquid, solid liquid combination. So that condensed phase is negligible. We don't consider that phase change. Okay. And then the third assumption is ideal gas law with constant specific heat can be applied. And then the fourth assumption is no heat transfer from the rocket engine, means the system is closed system. As you know, in thermodynamic system, if the system is closed, there is no heat transfer from the from outside to inside and from inside to outside. So that we are using an appropriate shielding material, means that shielding material means heat resistance material at the combustion chamber, so that heat transfer is protected. That is another assumptions. In actual, there may be a small heat exchange in between material may take place, but that will not be considered here. And the fifth one is uniform flow properties. These properties are the pressure, temperature, and density at nozzle entrance. Nozzle entrance means, as I told you, nozzle entrance is this position. This PT2 means the nozzle entrance pressure. which is high pressure here. So this is called nozzle entrance. Velocity at the nozzle entrance is negligible. Look, what we have discussed here, the velocity at nozzle entrance around here is very small. Because of that, high pressure is there, but velocity is very less. So that we consider it is negligible. Okay. Gas composition across the nozzle remain constant. Even though there is variation in temperature, there is variation in pressure, there exists a small composition difference, but we consider the gas composition or the high eject gas compositions throughout the nozzle remain constant. And the gas leaves nozzle exit along the axial direction only. Means actually the gas flow is towards to the outward, but still there is a kind of erosive pressures are there. Means pressure always act in perpendicular direction to the surface, but we consider only the axial direction for our analysis. The perpendicular one or the one which creates kind of hoop stress are not considered here. So from this all assumptions, let's consider the entrance region properties. Here HT2, the temperature T2, these are related as the exit region. No, entrance region. Still, please give emphasis for this thing. This is entrance region, this is exit region. Okay. Entrance means the hot particle gas is entering into throat through the divergent region. So that is known as the entrance region. So whenever you see T2 temperature to that are entrance region. TE is the exit region. Look, we are correlating the entrance and the exit only. But in actual case, we will correlate the combustion chamber phenomena with throat phenomena. Okay? Yeah. የላክልኝ አይቼዋለሁ ፕሪንት አድርጌ ሳይን አደረግ አሁን ኮንታክት እናደርጋለን። So what we are relating here is the entrance region with the exit region. Okay, so the heat of what we call the enthalpy at entrance region, which is equal to Cp T2T plus velocity at that particular point over 2. But this velocity is very small at point 2. Okay, at entrance velocity is small, and which is equals to entropy at exit, which is Cp T2. So here velocity is high, but temperature is less at this point. But in this case, temperature is very high because it is combustion chamber temperature. At the entrance region, combustion chamber temperature is considered. At exit, almost to the ambient temperature, so that this component is negligible here at the exit. But so they are compensate to each other. This is kinetic energy. It is just a kinetic energy, V square over 2. Okay. So kinetic energy relation. So we need to analyze the rocket nozzle by simplifying the complex flow with the assumptions. So the above assumption helps us to consider the phenomena. So by applying the energy equation between station two means entrance and exit, we have this relation. Okay. Now from that, we have to calculate the exit velocity. At exit, velocity is very high. As I told you. but this CPT2 is small. Whatsoever, from these relations, we can find exit velocity is equal to 2 times CP. CP means specific heat at constant pressure. Okay, you understand, you have to understand this thing. Times T at 2 minus T at exit. Okay, so now we can relate this temperature at 2 and the temperature at exit by the in the relation with gamma. That means the ratio of specific heat. So using that formula, you can find VE is equals to 2 times gamma over gamma minus 1 times the gas constant RU times temperature at that 2 divided by this is actually M or R. Yeah, this is just M. It is not M times W, but M. Okay, so that is molar weight of gas. Simply, it is molar weight M. So which is times 1 minus P exit over P entering region, the power of gamma minus 1 over 2. So this is exit velocity. Okay. And this RU is the universal gas constant, which is 3187 like that. Okay. And what we are, if we know if we have information of pressure at exit and pressure at the entering position or the inlet, we can simply calculate this formula. So this is the fundamental formula in our case. Either this one, or you can consider this one for further discussion. So the maximum exit pressure, because once we consider pressure at exit is equals to 0, because at exit there is high velocity rather than pressure. Okay, so once that is fine, okay, PE over PT2 is tending towards to 0. Then by multiplying, look, what does it mean? Exit pressure is almost 0 when we consider it with the entering pressure. The entrance pressure is too much high. The entrance velocity is too much less. So this value tend to 0. So 1 minus 0, this thing, the power of 0, the power of something is meaningless. So this will be neglected from the system. We have left only this component. Okay, 1 times this component. So that gives you the exit velocity, maximum exit velocity, which is equals to 2 times gamma over gamma minus 1 times RUT T2 over MW. This MW is specific mass. That is not specific mass, but it is molecular weight of the gas. Okay, so and if we want to see the V exit over V exit maximum ratio, then we can have this relation. Okay, this V M exit is this component only. So the relation gives us 1 minus PE over PT, the power of gamma minus 1 over R. That is, so the variation in velocity ratio for 3 specific ratios is plotted here. These are the floats. Pressure at 2 over pressure at exit versus velocity at exit over velocity at velocity max. So for actually these are some values of, it is just gas constant, various gas or various chemical compositions which we are taking will give us various value, different value of gamma. So gamma 1.2, 1.3, 1.4, and most gamma values are around these values. Okay, so in relation to gamma values, the float of pressure ratio to velocity exit over exit maximum exit velocity is plotted in this graph. So this is the effect of pressure ratio on VE over VE max. Okay. Okay, another important thermodynamic relation for the relation between V max, velocity, exit velocity max in meter per second versus a specific heat ratio, gamma. Gamma can be 1.1, 1.2, 1.3, 1.4. So that is some gamma value. Here also you can see same quantity, but yeah, as gamma becomes high, what is the value of VE max and the VE? So this is VE, this is VE max. Okay. If I took this point, where is our VE? VE max is somewhere around here, and our VE is around here. So there are some value difference, VE and VE max. Okay, so another thing is the conservation of mass. Okay, mass flow rate and characteristics of characteristic velocity. So in convergent divergent nozzle, the mass flow rate is constant actually. The mass flow rate through convergent divergent nozzle under steady state condition is which is dependent on pressure, temperature, and the velocity actually of the combustion chamber. So it is dependent on chamber pressure, chamber temperature. Okay, and the cross-sectional area also have its own effect. So you can see density, cross-sectional area, and the volume. Okay, no, the velocity, this is the velocity, okay? That is flow velocity at any location in the nozzle, so which is constant. So this is called conservation of mass. M dot is equal to rho A V. M dot means propellant mass flow rate. Here it is not the another mass, but it is just the propellant hot gas flow rate, which is equal to rho AB, like the fluid flow in the duct. So m dot is equal to rho AB, which is constant. Okay, rho is the density of the fluid or the gaseous fluid. A is the cross-sectional area of the combustion chamber. V is the velocity at any location in the nozzle. So from that, we have rho over P is equals to, no, rho over rho at interval zone T2, which is equal to P over P at intervals, the power of 1 over gamma. So the relation between density and the pressure is, it is like that. Density at any specific point divided by density at interance. Let me call it as interance zone, which is equals to pressure at any location divided by pressure at interance, the power of 1 over gamma. So this is the pressure density relation. Again, we have pressure temperature density relation. The density at any point divided by density at inlet. Let me, once we know the inlet pressure, inlet, which is equals to temperature at any position divided by, temperature at inlet, the power of 1 over 1 minus gamma. So this is density temperature relation. This is density pressure relation. So this is what we have discussed even in the previous section. Okay, so now let's consider uh, from this calculation, density is equal to mass over, actually this is mass flow rate in meter per second divided by area, which is equals to pressure times, you are familiar with this formula. This formula is the exit velocity. Okay, so what it is, m dot over, no, let me undo it. Okay, we have this relation, this formula, m dot is equals to rho a v, and once you understand the exit velocity, the formula for exit velocity is already given there. So let me bring this a here. So this implies what? M dot over area is equals to, which is equals to rho times V. Now let's consider exit area and the exit velocity. So let me say this as exit velocity, this exit area. Then we have formula for exit velocity. So combining that, exit velocity formula is this one. This one. 2 times gamma over gamma minus 1 RU T2 MW times this T. So let's substitute these equations together. So when we substitute these equations together, what we can obtain is this thing. Okay. Instead of density, we can substitute pressure. Okay, pressure. Here it is density. So we can define density in terms of pressure. So this means what? Okay, density T2. So finally that relates us to the density. So density will be here. So we have 1 over RT2. So yeah, that is just relating the density, pressure, and the mass flow rate equation. So this is the final equation for mass flow rate divided by area is equal to pressure at the throat entrance and times square root of gamma, 2 times gamma over gamma minus 1, the whole times 1 over RT2 times pressure over pressure 2. This is just 2 times the power of 2 over gamma. And then from that, this is just the velocity relation actually. So what finally we can get? M dot times radical of RT2 over area times PT2, which is equals to under square root of 2 times gamma over gamma minus 1 times pressure ratio at that particular position, the power of 2 over gamma, times 1 minus P over PT2, the power of gamma minus 1 over gamma. So this is one of an important formula. So this shows that the variation in the non-dimensional mass flux through the nozzle, which is floated here. It is in relation to pressure at any particular point divided by pressure at entrance versus the mass flux rate here. Okay, this is the mass flux rate. So for supersonic, for subsonic regions, for various values of gamma, it is plotted like this. So this is actually the pressure ratio corresponding to maximum mass flux is given by this formula. This is pressure ratio for maximum mass flux. Okay, so and this m dot over area at throat area. This is actually throat condition. AT means throat area. So why we are considering that throat area? In that region, that is critical position. Throat is one of the critical position in our discussion. So under which flow is considered to be aerodynamically choked. So this is the choking will take place. Like choking when we are taking food or water, sometimes we may feel choking in our throat. Similar to that, when there is high compressed gas or high gas is coming and accelerating through the throat, that the narrow region, it tends to choke. So that at the choking condition, the mass flow rate versus area throat is given by this symbol is symbol for gamma times 2 over gamma plus 1, the power of gamma plus 1 over gamma minus 1. So for that, we represented this kind of symbol. So we can find m dot over mat, which is equals to this quantity times pt2 over radical of rt2. So this is the choking condition, where at is the throat area of the convergent divergent nozzle. So this may be noted that critical mass flux is depend on area of throat. It depends on chamber pressure. It depends on the combustion chamber temperature and the specific heat ratio. So this indicates the critical mass flux dependent parameters. Okay. Now pressure at entrance is, you can just rewrite this equation and finally what you can get. So just bring this equation here. So you can find the pressure at throat entrance, not exactly in the throat, but at the entrance. This T2 is entrance. Okay. And the mass flow rate is in relation to characteristic velocity, C star. We have defined this C star in the previous lecture. So it is defined in terms of C star. So m dot is equal to pt2 at over C star, where C star is radical of RT2, the throat entrance over the symbol. Can I call this symbol as gamma or something? Because we have another gamma. So let me call it as rho, because it has no defined meaning, but it is just the indication of some parameter, this parameter. It is indication. So this is the C star value. Okay. So we can calculate C star from this equation. So from the above formula, what we can say is the characteristic velocity C star increases with adiabatic flame temperature, because C star is directly related with adiabatic flame temperature. And it is decreased with molecular weight of the gas. Actually, this is just considered molecular weight of the gas. And R is the gas constant. It increases with decreasing value of specific heat ratio. Why? Because specific heat ratio is related with this symbol. So we can see specific heat ratio. It is just a function of specific heat ratio here. So once we discuss this, maybe the time may not allow us, but we can add more time to calculate or to find to have some worked example. So it is just 1 minute is left, but let me read it and we will redo it. So in a convergent divergent nozzle with throat area of 0.5 of rocket engine, gas at 5.75 megapascal and temperature of 2800 Kelvin is expanded fully to 5.5 kilopascal for producing thrust. Assuming fluid flow to be isentropic, determine the exit Mach number. One, exit Mach number, that means ME. Two, the maximum exit mass flow rate passing through this nozzle, and the third one is the exit area. Okay, assume gamma is 1.25 and MW is equal to 0.5 kilogram per kilogram mole. Okay, so this is a given parameters. Then based on this parameter, we can find the Mach number. Mach number is related with the velocity. Exit Mach means exit velocity relation.